Oh, hi everyone. My name's Sebastian. I work for Penn State University, and this is where I work when I'm doing remote access. It's nice to meet you. So let me go ahead and introduce you to some of my equipment here. This is the FESEM. It's a field emission scanning electron microscope. The first screen on the left is my main screen for interacting with the FESEM software. The second screen is connected to the same computer and allows me to better multitask. Now the screen furthest to the right is connected to another computer and is used for EDS X-ray detection. So yeah, without further ado, let's get started learning about how to use our FESEM. By the way, the bulk of the screen, which you see right now, is covered with the FESEM software interface. This is the desktop which I view when using the FESEM, and it's also the first screen that you'll see if taking part in a remote access experience. Here is a front view of our Zeiss Ultra 55 Field Emission Scanning Electron Microscope, or FESEM for short. At the top we see a large electrical cable which is used to carry the high voltages necessary to generate an electron beam. The gun and gun column are housed in this part of the instrument. This is where a large voltage is passed through a sharpened filament and an electric field is generated, all in order to extract and emit electrons down towards our sample. The pressure in this part of the chamber, the gun chamber, is usually around 10 to the negative 10 torr. As we travel further down this column, if we could see inside, we would be viewing many essential components of our FESEM. Remember, the beam originates from the electron gun. Below this are the anodes, which serve to draw the electrons out of the gun and also change the accelerating voltage on the electrons, therefore giving them greater or lesser energies and velocities. Below this is a magnetic condenser lens, which serves to change the size of the electron beam as it passes through its center. Just above this, not shown in this picture, would be various apertures, which are used to block outer sections of the electron beam. Next would be deflector or scanning coils. These are used to raster the electron beam across our sample. Below this would be a in-column BSE or backscattered electron detector and an in-lens secondary electron detector, which is not shown here. This figure also shows a side-mounted secondary electron detector. And lastly, also not shown here, would be our objective lens. On the right, we can see two tubes, which are essential components of the BSE and in-lens detectors we just mentioned. Their job is basically to convert incoming electrons into a photonic or light signal, which is amplified and then converted back to an electric signal before being sent to the computer monitor. Each of these tubes consists of a scintillator, a light guide, and a photomultiplier. On the left side of our tool, we see our Inca EDS X-ray detector. EDS stands for Energy Dispersive Spectroscopy. Whereas all the other detectors on this tool are used to detect electrons, this EDS X-ray detector is used to detect X-rays. This is considered an analytical detector because the energies of the X-rays emitted from a sample being bombarded by electrons are characteristic of the elements present in that sample. In other words, if it is known that a certain element such as iron, with the symbol Fe, emits X-rays of energies 6.5 and 7 keV, then we would expect to see peaks at these values. Therefore, this tool makes it possible to figure out the precise location and identity of various elements within a sample. Just behind this, we see another detector. This is another secondary electron detector, but instead of being mounted in lens, this detector is mounted on the side and on an angle, and it's often referred to as an Eberhardt-Thornley detector. Because of its mounting in position and distance from a sample, it provides us with a more topographic contrast, but less edge resolution than an in-lens detector. Now let's take a look at the inside of the chamber. At the front of the tool, if we open the chamber door, the first thing we will see is the stage with some samples loaded on a circular carousel. Just behind this, we see a few things of importance. The metallic cone in the top center of the screen is actually where the electron beam exits the column and travels through several millimeters of free space before interacting with our sample. The vacuum within this region of the tool, the chamber, is usually around 10 to the negative 7 torr. If we could see inside this cone, we would see two detectors. One is an energy selective backscatter electron detector, and the other one is our in-lens secondary electron detector. Near the center of the screen, just to the right of the metallic cone, is a small black hole. Behind that is an infrared camera. This camera is actually used to give us an interior view of the unlit specimen chamber. Here on the top left, we see the end of the Inca EDS X-ray detector, and just below it, we see our side-mounted secondary electron detector, also called an Eberhardt-Thornley detector. The small wire cage you see around this detector is actually used to apply a grid bias. This is used to apply either a positive or negative bias in order to attract or repel electrons towards the detector. As we make our way back out of the tool, we again see the stage and our loaded sample on the carousel. We can close the chamber door, take a few steps back, and that concludes our discussion of the main hardware components of our FESEM instrument. Here we see a typical sample holder. This is a 9-stub sample holder, which is capable of holding up to 9 different samples. The back of each sample holder is fitted with a metal dovetail that allows us to accurately load and center our samples for investigation. All that's required to load a sample is to make sure that our chamber has been vented to atmospheric pressure. Then we open the chamber door, slide our dovetail onto the stage, close the door, and we're ready to begin. Here's that same procedure, but from another angle. This angle is showing the view from within the chamber itself. At the lower left, we see a scale bar. To the right of here, signal A is telling us the detector that we're set at. EHT is telling us our accelerating voltage, file name if we were to save something, our current magnification 54 times, and our working distance 4 millimeters. By clicking on this button, we can change from coarse to fine control. By clicking on this vacuum tab, we can shut down the gun or pump. By clicking on the gun tab, we have the same options in this case. And by clicking on EHT, same options in this case. But they're telling us a red X is not okay to go. Green check is okay. At the top, if we look at the Detectors tab, we can switch detectors by clicking here. We can also mix detectors by clicking this little box, and we can change the ratio of signals. We can also change the brightness and contrast here. If we click on the Scanning tab, we can quickly change the scan speed from 1 to 15, and we can also tell it to freeze on end frame and change the type of scanning. Under vacuum, we can see at the top right there is chamber vacuum, and below that gun vacuum. Here we can see the current stage coordinates. Under the Apertures tab, we can change apertures, 30 microns, 10 microns, 60 microns. We can also do aperture align here. Finally, on gun, we can see what the EHT value is set at, and a couple other incidentals which we don't really want to change right now. This icon allows us to reduce raster. This one allows us to change our focus. TV will take you to the chamber view. The mag button will allow you to play with magnification. Here's a brightness and contrast, stigmation icon, stage center, which will center on a feature of interest. Normal, take you to a normal scan speed. Export will allow you to save a file. Then line and frame integrate are different types of scanning to create a picture. And we can change our scan speed quickly here, and also change our accelerating voltage quickly with use of this icon. Since we just loaded a sample, the first thing we'll have to do is pump down our chamber. We can see that the gun vacuum is okay to go, but the chamber vacuum is not quite there. By clicking on this pump button, we will begin to pump down the chamber. Now, through the magic of editing, we can see that the pump vacuum is about to kick on here. This actual process takes about 5 minutes. The vacuum will continue to pull, and we will not get an OK on the vacuum tab down at the bottom until we're at normal operating pressure. Okay, once at standard operating pressure, we get the green check mark on our vacuum tab. We can now turn on our EHT, which means we can establish an accelerating voltage. Notice the blue bar in the bottom of the screen where it says running up. This is designating that the accelerating voltage is ramping up right now. And finally, we have all green check marks on our tabs below. Let's just double check. We'll click on our gun tab. We see we have an EHT of 1 kilovolt. Investigation of a sample often requires movement of our stage. There are several ways to do this. One way is with the joystick controls. We can tilt the sample right and left by moving this joystick. We can also raise it up or down in the Z-axis. The knob on the right allows us to move this stage in X and Y directions. This knob also allows us to rotate our sample about the Z-axis. There are other ways to move our stage, however. One way is by clicking on Soft Joystick to bring up the Soft Joystick dialog box. Now we can perform the same movements. We can move the stage up and down in the Z-axis, We can tilt the stage, and we can also rotate the stage. We can also simply use the stage vector control to move the stage in the X and Y axes rapidly. Yet another way to control the stage is to open up the stage navigation control window. This provides us with the side and top-down view of our carousel and allows us to select our sample of interest simply by clicking on it. If I double-click, the stage will recenter on that sample. If your sample has been properly loaded, your chamber is under vacuum, your accelerating voltage is on, and your working distance is correct, but your image still appears like this, then you know that you need to adjust both your brightness and contrast. When viewing the SEM control window under the Detectors tab, we can see our brightness and contrast levels here. There are actually several ways to adjust these. We can do this manually with the keyboard control knobs by simply moving them right or left, and the typical desired brightness will be between 45 and 50% brightness. Once here, adjust your contrast until the image appears most appealing. At this point, it may be necessary to go back and forth one more time, adjusting both brightness and contrast if necessary. Of course, we can also adjust these parameters through the software interface by sliding these buttons here. We can adjust brightness and contrast by sliding the buttons right and left or using the individual arrow keys. One thing to mention is what these terms, brightness and contrast, actually mean. Well, brightness is actually representative of how much your electric signal is being amplified. So by adjusting brightness, we are simply changing the amplified signal coming from the photomultiplier tube at the end of each detector. Contrast, on the other hand, is not signal intensity, but the range or spread of intensities as they are displayed on the screen. We typically want a large spread or dynamic range in order to produce the most visually appealing image. Another important factor to consider when viewing your image is the scan speed. The scan speed is basically how fast the electron beam is rastering over your sample. By clicking on the Scanning tab and then Scan Speed, we can choose different scan speeds. The lower the number, the faster the scan speed, and you'll see the quality of your image change. If we go to a higher number, we would expect a slower scan speed and therefore a higher quality image. Yet another way to control the scan speeds is by pushing the plus or minus buttons on the FESEM keyboard. One last thing to mention is that a quick way to return to a typical scan speed of 3 is by clicking on this normal icon. That'll always return you to scan speed 3. To quickly navigate about your sample or center on a particular feature of interest, there are a few options available. The easiest way is to simply click Control and Tab at the same time. This will bring up a green cursor. Now if you left mouse click on a feature, the screen will center on that feature. Another way is to simply use the actual hardware joystick, which you're already familiar with. Still another way is to use the soft joystick, which you were also previously introduced to. But again, Control Tab is probably the most straightforward and simplest way to center on a feature of interest. One more option is to click on this icon called Center. After that, you get the green crosshairs. Simply click on the feature of interest, and the screen will now be centered. If you want to view another feature, click Center again, click your feature of interest, and the screen will be centered. Magnification can be altered in several ways. This magnification knob is a simple scroll wheel. It allows us to magnify our image by moving it clockwise or counterclockwise. Of course, this does nothing to alter or fix our focus, but it does give us the ability to quickly zoom in and out on a sample. To view our current magnification, we can look here. If we double-click on this number and enter a new magnification factor, then hit OK or Enter on the keyboard, we will again change the sample magnification. I've entered 100x, and we now see that our image is at 100 times magnification. For software control of magnification, make sure you have a 3-button mouse with the scroll wheel in the center, and click on the Mag icon. Now simply left-click somewhere on your image and use the scroll wheel to either increase or decrease magnification. Focusing on an image is very similar to changing magnification, at least operationally. One way to focus is by using a focus knob. Again, by rotation of this dial, we can bring our feature into and out of focus. One note of importance is that as we adjust the focus of our image, we're not moving a glass lens closer or farther from our sample as in an optical microscope. All that we are actually doing is adjusting the strength of the magnetic field emanating from the objective lens. This serves to adjust the height of the focal point of our electron beam. Another thing to consider is that at low magnification, it's very challenging to determine whether or not our image is in focus. Therefore, it's good practice to adjust focus and magnification several times while viewing smaller and smaller features on a sample of interest. If we increase our magnification, adjust focus, and then repeat this process, increasing magnification and adjusting focus, we'll end up with the highest resolution and most in-focus image we can get at a higher magnification. Software control for focus is very similar to magnification. Simply click on the focus icon, click somewhere on your image, and now use the scroll wheel to increase or decrease focus. For fine adjustments, simply click on the Coarse button so that it now says Fine. Now you have fine control. This action also enables fine control for all major software adjustments. In order to make operation of the FESEM more user-friendly, One option is to reduce the raster. We can do this in a few ways. One way is by simply clicking this Reduce button. This reduces the sample area over which the electron beam must raster. Another way to reduce the raster scan size is by pushing the Reduce icon located here. Again, this serves the same function as pushing the Reduced Raster button. Obtaining a clear image is relatively simple. Once you have your working distance, brightness, contrast, and mag and focus somewhat figured out, then we can go ahead and zoom in on our feature of interest and begin to get a nicer image. Typically we would start by going to scanning and decrease the scan speed. In this case, I'll go to scan speed 7. Now we can either choose to freeze, or it will simply freeze on end frame, and we'll get a nicer view of our image. By changing the scan speed, what we did was increased the amount of time that the electron beam spends rastering across the sample. Now let's go ahead and unfreeze this image, and now we'll return it back to something like scan speed 3. Let's try something else. Let's do a frame average with n equals, let's say, 66. What this will do is it'll have the electron beam raster across the entire frame, repeat that 66 times, and basically take a pixel average. Another option is to do frame integrate. Let's go ahead and choose that and increase our n number, which is the number of integrations. So now this is doing somewhat of a mathematical calculation while integrating the pixel information coming over from the entire frame being scanned 54 times in this case. Another great option is line integrate. Let's choose that, do something like n equals 50. What this will do is scan line by line. So it'll scan one line 50 times, then move on to the next. This is a very important method for obtaining an image, especially if your sample is non-conductive or prone to charging. When we're all done, the last thing we'll want to do is turn off our accelerating voltage. Notice the blue bar running across the bottom of the screen. Once that is run down, we get the red X. And now we can go ahead and vent the chamber in order to remove and perhaps load another sample.